Good morning, everyone. I'd like to thank the organizers for putting this event together and for giving me the opportunity to speak here. I'll be talking about a piece of work I've done together with a postdoc, Federico Balducci, at MPI-PKS in Dresden, and Anusha Chandran, who was spending her sabbatical with us last year. And here's the reference to this work. So, motivation is the study of 2D quantum dynamics. So I will say a few words about this, but I suspect given you are here, you're almost sold on that idea already. Then I'm going to explain a particular experiment that got us to think about this, present an effective model. Then the main result is going to be notion of symmetry rebreaking, which appears, and then I'm going to say a few concluding words. Okay, quantum computers are developing at very high speed, and people discuss a lot quantum advantage and so on. It's also the notion of quantum utility, which is that NIST devices are at some point getting close to being platforms of choice for studying particular types of questions. And this is especially true from a theorist's perspective. So the kind of perspective I take on this, if an experimentalist comes to me with a data set, I don't ask, how long has this taken you and could I have done it faster in a classical computer? I thought, wow, this is really excellent. Let's think about this. And on that level, quantum computers are really pretty close to actually working with real experiments right now. And also in work with Matteo, we did say a few years ago that at the present stage, a good way of thinking about NIST platforms is to treat them as not imperfect quantum computers, but extremely coherent experimental platforms. And for these, many-body physics is a non-trivial, yet at least partially understandable framework which look at things, so you can use it as a benchmark because you can actually formulate certain expectations of what should happen, and you can see whether they are realized in experiment, and if no, what is going wrong in inverted commas. And in that sense, this effort is a two-way street. And of course, this is not going to last forever, because at some stage the NIST devices will continue to develop so that we're no longer in a position to provide this just as a benchmark. But of course, then we are crossing over into a regime where we're really using NIST devices in discovery modes, that is to say, where they're going to find things that we really, really haven't thought about. Okay, so fundamental questions in quantum, especially in higher dimensional quantum simulations, and there are quite a few topics which have been studied in the last couple of years. I'm going to focus here on post-quench ordering dynamics, which I'll motivate in the next few slides. Okay, so just the reason why 2D is sort of different from 1D is that in 2D, in a very direct, very simple, and very general way, interfaces, i.e. one-dimensional degrees of freedom embedded in 2 dimensions, appear very naturally. So just think of a quantum easing model. A quantum easing model can have symmetry breaking, so there are domains of upspins, domain of downspins, and they're separated by domain walls, which are these one-dimensional sort of topological objects. One can start studying their dynamics, and there have been a few works on this already. And so taken together, there's basically the question: what is the quantum dynamics of domain walls in 2-dimensional systems, where they are sort of play the role of point-like domains in 1 dimensions, and in that sense they're really different from the 1-dimensional problems, and they can exhibit new physics. Okay, so what happens to interfaces at long times? So classically, if you're sitting at low temperatures, a minority bubble is well known and has been studied for a very long time to shrink at low temperatures. And so this is the question: how does order emerge in time? And so this goes under the names of domain coarsening and phase ordering kinetics. Quantum mechanically, there's also been some work, but this is not so easy to describe. And but one can, in just the same way in quantum mechanics, ask, how does order emerge in time? So typically, these coarsening experiments are looked at when one quenches from high to low temperatures across a phase transition. In a classical setting, there's a scaling hypothesis, and essentially 0 and finite temperature aren't all that different because they've got the same long-range order, which exists on infinitely long length scales by the definition of long-range order. And then you can ask, how does this long length scale get established if you start with a system which only has correlations on the shorter length scales? Okay, so if you have, say, 2 phases, shown in different colors here, and no bias between them at 0 time, then this coarsening process can go on until very long times. And this, again, as I say, has been studied in considerable amount of detail. Okay, so if you ask about quantum mechanical states, you can basically see, well, if there's order at 0 temperature in the ground state, you don't have any non-trivial dynamics. The system just sits in its ground state and perhaps oscillates between 2 ground states or so, but that's it. However, if you do a quench, you typically end up with a finite energy state, and then you can basically ask what is the effective dynamics in the setting. The energy density can be very low, so you can already ask a question if you've got a thermodynamically large system with only order 1 domain walls, then the energy density is 0, or you can have just very well separated domain walls, and so that the energy density is very low, and then you can hope that in some sense you're still probing quantum critical behavior as you quench the system across or close to a critical point. Okay, and some experiments have been done here. So I'm showing here 3 from the year 2025. And our interest focused on some qualitative findings in the work from Harvard, which I'm going to describe in the next few slides. Okay, so here's the quantum coarsening experiment. So this is done on Rydberg atoms. Rydberg atoms are either absent or present on a side of a 2-dimensional lattice. The lattice is 16 by 16 sides. N equals 0 is absent, n equals 1 is present. There's a hardcore repulsion. So there's a nearest neighbor repulsion between these, which has been chosen so that the repulsion is strong and only on nearest neighboring sites, and it's more or less negligible for further distances. So there's a field which favors the presence of atoms, and then there's a transverse field. Okay, and so this maps onto essentially an Ising magnet, but it's not an Ising magnet in the sense that you break the symmetry between occupied and empty sites, Ni, but that you basically, if you favor the occupancy of sites very strongly, then the system wants to go into this highest density state that it's available, but the nearest neighbor repulsion means that you can go at most to half filling, and the half filled states are checkerboard states. There are 2 checkerboard states related by simple translational symmetry, and these 2 checkerboard states, okay, if you enter one of these, this is an Ising symmetry breaking, and I'll be using the language of Ising ferromagnets in what follows, even though microscopically you're actually breaking a translational symmetry. Right? There's obviously no particle hole symmetry here. Okay, and then if you look at this, so here is this checkerboard state which is ordered. You can tune the ratio of the detuning to the strength of the transverse field, and then you see that if you are sitting close to the critical point, you start by seeding a droplet of the minority phase inside the majority phase, and you see that with different speeds these disappear. There's also some other physics which happens here, but you basically see that the smaller the delta over omega, the faster the disappearance of this high dense or this well-ordered droplet in the center. Okay, and just to put some numbers on it, so here you see the growth of the largest domain, which goes, so this is a system of 256 sites, starts from having just about more than half, and then increases, not by a huge amount, and whereas the second largest domain, so the minority domain, basically starts shrinking. So you immediately see these are not gigantic systems. It's not clear whether the language of scaling functions and so on is particularly appropriate here. You certainly don't have decades of signal that you can work with, but nonetheless, I think it's important to realize that these are real data and they really give you things to think about. And even though they may not be perfect in what we want, I think it's one of the it's very encouraging that these kind of systems are now available to probe physics on, after all, 256 spins, and to give qualitative information about what's going on. Okay, one thing that was in particular, so there are several things which were studied experimentally here. One is a slow ramp through the critical point, and doing this by measuring an appropriately defined order parameter, what was found was that there were oscillations after this ramp had taken place, both in the order parameter and in the correlation length. And in another thing, the model was started very close to the very strong field where the order is almost perfect, and then quenched into the antiferromagnet, closer and closer to the transition. And again, what was found is an order parameter which oscillates and a correlation length which oscillates. Extracting information from that, so the frequency of the oscillations is plotted here. So this here is the disordered phase, and sorry, this here is the ordered phase, and that's the disordered phase. So what you see is an asymmetric shape of the oscillation frequency, and you see a damping which appears to be maximal, not at the phase transition itself, but rather to the side of the phase transition. Okay, and so it was noted that this gives you a lot of information which is hard to access otherwise, and so given there were some nice qualitative results here, we decided to try and see whether we could come up with an effective model explaining all of this. So in the next few slides, I'm going to be introducing the effective model. Okay, so we're going to model this as a classical transverse field easing model. Here's going to be 2 slides of justifying this, but this is the basic upshot. So we start with a 2-dimensional transverse field quantum easing model. Basically, it's got the right symmetries. It's got an easing symmetry breaking for large J and an easing symmetric state for large G. And it's got a dynamics which is well known in terms of the Pauli matrices. If you want to justify making the transition to the model that I just said that we were going to use, you can think of doing some coarse graining so that you no longer have spins a half, but that you've got larger spins so that you get renormalized values of the exchange in the transverse field. And then you actually treat this as a large spin problem with a essentially classical dynamics given by the Poisson brackets, which is inherited from the commutators from the quantum model. And then what this dynamics basically then describes is that each spin has an effective local field, which is the sum of the exchange field due to its neighbors and the transverse field, and it processes around this. That's it. That's the dynamics of the model. So it really is very simple. So here is this processional dynamics and the effective field. Okay, now I'm going to explain to you how the phenomenon of symmetry rebreaking actually appears in this setting. So this is going to, just to formulate things again. So the goal is that after quenches deep from the antiferromagnet, which is where we found qualitatively things are easiest to understand, we have these oscillations in the order parameter, and I'm not going to show you any data about the oscillations in the correlation length, even though we also can account for this in our theory. Okay, can we develop a theory for these oscillations? Okay. So this is what these quenches look like. So you can have an energy density, which you can also think of temperature in some sense. You've got the transverse field. So if you start at 0 transverse field, you're essentially starting in this perfectly ordered Niel state where spin, or ferromagnet in this case, where all spins point either up or all spins point down. You then just change the transverse field so that in parameter space you go to the right. But since the initial state is still this perfect ferromagnetic state, it actually corresponds to a finite energy density. So as you change G, you actually trace out a trajectory in this phase diagram where as G increases, the energy density goes up. As I'm going to be showing what happens if you quench G to various values along this line. And finally, there's a thermodynamic phase transition, and when you cross this, you go into the paramagnetic phase where when you finally thermalize, it's you're in the disordered phase. Okay, and so just very, very simply, why is there dynamics in the order parameter when you do this? And this is completely trivial. You start off, all the spins point in the z direction. You change the magnetic field, the transverse field, so that the sum of the exchange field and the transverse field is no longer along the z direction, but in a different direction, so that there's a net field now here. And then the spins are going to process around the net field that they are seeing. So this is basically where the central ingredient to why there's dynamics after the quench, and we're going to study this dynamics in more detail. So I've tried to give you a justification of this. I think sort of morally, you should think of this description as capturing the dynamics of domains which are sufficiently large that you don't have to worry about what happens in details at the fringes, and of course what happens in details at the fringes is going to determine what the actual long-time behavior is. But yeah, what I'm going to do is basically tell you how to understand the oscillations to start with, and then how they get degraded as the next step. Okay, so we can simulate this dynamic straightforwardly. So you see, if you quench to this point here, you have a few oscillations which die out, and you remain in the ordered phase. If you quench into the disordered phase, then you again have a few oscillations, but they oscillate now around 0, and then they die out, so that you finally don't have an order parameter anymore. In between, things cross over, and they're not so easy to interpret immediately. So here you see at this point that there are some overdamped oscillations, and then you end up with an order parameter which points the other way than it started from. And if you go very close to the phase transition, then again you've got some oscillations, and finally you've got 0 order parameter. And so I'm going to explain to you how this comes about in the next few slides. Okay, so since you're starting from essentially translation invariant state, the fluctuations are very small at short times. So if you really put no fluctuations in at all, then the system would just be sitting there, and you would only get the Q equals 0 mode, so the uniform mode having any dynamics at all. So since you're close to this, the mean field description is pretty accurate. So we replace this by mean field treatment, where basically each spin sees the same environment. And then you may recognize this equation as essentially being a version of the Lipkin-Meshkov-Klick model, where you've got sort of a large spin in a large exchange field and a transverse field. And so this has been studied quite a lot, and I'm showing in light gray the data for the same parameters that you get out of the LMG model, and you see that they disagree at long time, so there's no damping in the LMG model. But the oscillation frequencies agree initially, and then you basically just have the nonlinear, so the dying out of the oscillations which disagree between the two. But the short time physics is clearly well captured by this effective long range model compared to the numerics. Okay, so just to make things not so easy, the x-axes on the experimental and our work are inverted with respect to one another. So small transverse field is on the left for us and on the right here. So the comparison actually looks a little bit better than is apparent at first sight. So for the frequency of the oscillations, you have this asymmetric line shape, so which is steeper on one side than on the other side. You've got the damping, which appears to be stronger away, which appears to be stronger. So, okay, let me just go a little. Okay, so first the two more or less agree. So you have the damping, which has a peak, which sits not on the phase transition, but to the side of the phase transition on the right here, on the left here. So it's on the same side in both cases. And so this has a number of qualitative features. Namely, there's a frequency minimum within the ferromagnetic phase, so away from the phase transition. There's an asymmetric shape of the oscillation frequency around this minimum. The decay rate is maximal within the ferromagnetic phase. The decay is not exponential of the order parameter, but it's rather different shape. And so what's the mechanism behind this decay? So I'm going to be discussing those next. So first of all, I'm going to address the question, where's the frequency minimum within the ferromagnetic phase coming from? And this is something you can already see easily in this mean field approximation, where in fact, for the LMG model, this is a phenomenon that had been known. So we start with all the spins pointing in the Z direction. The field then tilts so that for a weak tilted field, so the effective field then tilts as you switch on the transverse field. And so the spins oscillate, precess around the effective field. As long as the field is weak, they have a relatively small circle in which they oscillate around. But if the field is very strong, then they leave the hemisphere on which the spins pointed, and they basically explore both the northern hemisphere and the southern hemisphere of the Bloch sphere. Okay? So this is basically then a transition between the regime where you only explore the northern hemisphere and where you explore both the northern and the southern hemisphere. Between the two, there's a separatrix at this point here, where the spins only just reach the equator. And the reason that this corresponds to a minimum in the frequency is that as they reach the equator, they slow down, and the equator, a point on the equator itself is actually an unstable fixed point. Okay, so in other words, they take infinitely long to reach this point, and this is why the frequency becomes 0. Okay, and then if you're close to there, you basically get repelled either back into the same hemisphere or you change over into the other hemisphere. So this is an unstable fixed point. And that structure itself accounts for most of what we saw before. So here I'm showing you a very simple cartoon of how you can understand how these things act together, and then how you can also understand the role of fluctuations which dress all of this. So this is very impressionistic. So basically, here's the Bloch sphere where the mean field vector points, and then I'm just taking the azimuthal, the polar angle, which I'm plotting in this direction, and then I'm plotting sort of an impression of something that you might call a free energy landscape. So I'm sort of mixing single particle and many body physics here, but basically you can think of the order parameter as just as a function of azimuthal angle of living on a free energy landscape like this. And there are two things that you can tune. So one is the free landscape, which depends on the final quench parameters. So this is in the disordered phase where there's a minimum at 0, whereas there's 2 minima in the ordered phase. But then you can also change where you start the oscillations from. And so if you're starting them at relatively high energy density, there's actually no big difference between the ordered and the disordered phase. You're basically sitting at high effective energy density. And in the ordered phase, you oscillate from one side of the Bloch sphere to the other side of the Bloch sphere and then back again. So here I'm showing the extremal cases. Here, this is where you start. Here is where you turn around. And if you do the same thing in the ordered phase, you notice that there are 2 free energy minima, but nonetheless you go all the way from one side back to the other side, and therefore dynamically, if you take an average over this trajectory, there's no net order parameter. Okay, so you can go to the low into the ordered phase, and then you can also change the starting point. So most extremely, what you can change is the starting point now, which isn't up here, but which is at much lower energy density, and then you oscillate within only a single well. So you go from one side of the well to the other side of the well, and then you go back again. So this is just the oscillation, which is confined now to the northern hemisphere in the previous plot. Now, the separatrix you get if you start at the height of this free energy maximum. So you now oscillate down here and then back up again. And then as you do this, you eventually reach the fixed point here. So these two plots don't just are not just a representation of the temporal aspect, because the time it takes sort of the middle of this blob. So I'm showing here the initial state is not being perfectly point-like, but is having some spread in the energy density. And so this spread in the energy density on this side then corresponds to a finite spread here, so that part of the initial conditions actually do not make it to the maximum, but turn around before. A particular point in the initial conditions make it exactly to the maximum here, and the other part of the initial conditions make it across to the other side like this. So from this, you immediately see how the fluctuations get amplified and how the order decomposes. Because if you started with a fluctuation on the left-hand side, you stay locally in the northern hemisphere and you've got an up domain. If you're starting at slightly higher energy, you basically make it across to the southern hemisphere, and for part of the time, you point in the opposite direction. And then, of course, the times for the round trip to get back then vary greatly between these different initial conditions. So if I plotted this after a certain time, this spread would just get bigger and bigger, and you'd eventually cover the entire curve here. When that happens, of course, a simple mean field picture like this is no longer particularly useful. I'm going to address this in the next few slides. But notice that this very simple cartoon already explains a number of things. It explains the zero frequency. These are the initial conditions which make it up to here. It explains the maximal damping. So this is what I just explained here. So if you are spread around the zero frequency curve, then you fragment your initial conditions most efficiently, and that happens at the point where the zero frequency takes place. And it also explains the asymmetry of the frequency curve in an extremely simple way. It's almost embarrassingly simple. So if you're the right point, so just imagine you're a little bit below, here below this maximum, you go over there and then you go back again. Whereas if you're a little bit above, you go over there, you continue and you go all the way to the end, and then you go back again. So there's simply a factor of 2 difference in the time it takes you to make a round trip. And of course, if you then go higher in energy, this asymmetry gets amplified by things like the curvature and the gradients are different, but basically this is already enough to explain the shape of the curve that you see here. So here is, so if you were to resolve this here more carefully, there would be a factor of 2 different in the slope of what looks infinite here, and then you get, just from the dynamics in this landscape, you get the explanation of the frequency dependence of the oscillations. Okay, so let me focus on the point that I made here, which is that if you're starting sufficiently close to this dynamical phase transition, your system sort of fragments. Parts where the local fluctuations were to higher energy density flip their direction with respect to parts which were at lower energy density, and then this is what looks like that. So here I'm showing quenches to 2 different points, both close to the phase transition but within the ordered phase. So you see there these oscillations, and as the fluctuations get amplified, your original ferromagnetic state actually decomposes into this mosaic of up and down states. So here, for only very small differences in the final quench parameter, you see that the intermediate regime looks very similar. But then at long times, actually coarsening takes place, and for some initial condition, the coarsening goes towards an up state, and for the other initial condition, the coarsening goes towards the down state. So in other words, fluctuations destabilize the system exactly where the order is minimal, and then the order needs to be re-established within the phase via coarsening. So in other words, you go from the phase to within the same phase, but the final state may actually have a different symmetry breaking than the initial one. So without ever leaving the ferromagnetic phase, you actually get an additional symmetry breaking happening. This is why we call it symmetry re-breaking. The system is always symmetry broken, but it re-decides which direction it wants to point in. Okay, so if you look at this in more detail, there's what we call this sort of zebra pattern, depending on when the coarsening effectively starts as a function of G. And depending on energy density, there are regimes where the coarsening either takes you to an up or a down regime, and then if you're going to lower energy densities and closer to the critical point, you get this pattern getting narrower and narrower, so that at some stage you can no longer predict in any way which state you're going to end up with. So it's symmetry breaking in that sense. Okay, so very briefly, how does this hang together with a nonlinear analysis? How do we explain this non-exponential decay of the order parameter? And again, that is relatively simple. So basically, as long as you're uniform and with small fluctuations, you have a regular oscillation pattern. As fluctuations get amplified, your dynamics becomes less and less linear. That is to say, linearities grow, self-amplify, and so therefore, what you have, rather than an exponential decay of the order parameter, you've got an exponential increase of the fluctuations around the order parameter. Okay, so as I mentioned before, this the first stage, so before this nonlinear analysis, had been recognized in finite N Lipkin-Meshkov-Click models, and perhaps the really surprising thing in all of this is that what we've done actually works in a two-dimensional system where you might have thought that mean field theory isn't going to get you very far. To describe an actual quantum system, qualitatively and even semi-quantitatively, and its behavior that is seen for spin a half on a quantum simulator for a smaller system size, but the sort of basic questions that I formulated all occur in our effective model as well. Okay, so conclusions. We've looked at quantum dynamics in 2 dimensions, in particular the interplay with spontaneous symmetry breaking. There have been very encouraging pieces of progress in studying quantum coarsening and quantum quenches in this type experiments. We've discovered a simple model which works qualitatively remarkably well. And so this is an example now where where the quantum experiment has motivated a theoretical development which, when you look back, you can say, well, this was easy. All you have to do is write down a classical transverse field Ising model and you can account for the quantum experiment. But if we'd done it the other way around and we said, here's a classical Ising model, the prediction is this is going to explain what is happening in a spin-a-half transverse field Ising model, I think you would, with some justification, have said, I don't believe this until you show me considerable evidence. And so this is the evidence that we've tried to show you, and the important thing is the evidence and experiment came first. So in that sense, this is an experimental discovery with which we've accounted for theoretically. And I've suppressed a lot of details, but basically the symmetry rebreaking is the new phenomena that we've discovered, where you see that you can re-establish the order in an unpredictable direction without leaving the ordered phase. And there's lots of future things that can be done beyond that. Thanks a lot for your attention.
Thank you for the nice talk. I have a question about quantum systems. In principle, we should be able to go under the barrier and quantum tunnel. Mm-hmm. Do you expect to see any effects of this, and theoretically or experimentally?
Okay, it's a very good question. So my kind of gut reaction is that once your effective coarsening length scale is very large, having cooperative quantum tunneling around, a barrier, even if it's not very high, but which is very broad, is probably not going to play a huge role. That doesn't mean that in an experiment it doesn't play a huge role, because, after all, the experimental system isn't so big. And it would definitely be interesting to have run some direct tests of where one can discover quantitative, but ideally qualitative, differences in behavior in these experiments, which go beyond the simple theory that we've shown.
Roderich, can I just ask how much is tied to the specific model? Because I remember very similar discussions in superfluid Mott quenches, for bosons, Ehud Altman, Asa Auerbach, Anatoly Polkovnikov, Subesachev, 2002, 2004, which seem to have come up with very similar mean field equations, putting quantum fluctuations on top. I don't know, yeah. But do you remember this discussion?
So Subesachev was co-author of the experimental paper, yes. And he didn't seem to make the connection that is the same as 20 years ago. So,
well, yes, maybe that's why.
If it's his own work, right?
But you know these papers? I mean, because I think it looks at very similar at the discussion there.
Yeah. Okay. I know the papers, even though I haven't filed them. No, some of the papers okay. I haven't filed them under this question, but I would be interested to see. Okay. So you mentioned quantum fluctuations. The point here is fluctuations play a role, and I'd like to see this idea of symmetry rebreaking if it's there already.
This I don't know.
Yeah,
I have to go into.
Yeah, this is the important phenomenon. So, as we said here, so also including people in the room. So the general framework. So that's definitely not new, but this recognition that out of this very simple framework you can get this very qualitative behavior, I think is new, but yeah, I wouldn't be completely shocked if one of you were to get up and say, actually, in some paper I did 5 years ago, that was already there.
But the whole mean field discussion, is that, because that seems very similar to me than what was discussed.
No, so, the idea of using mean field theories for quenches and ordering settings is not original. It's certainly a lot more than 20 years old. Really the important thing is that, in this particular simulation, there were claims that specific features could only be understood in a particular quantum framework. And so we were basically then asking how far can we get using conventional methods. So I would not advertise the methods and the concept as being the novel thing here, but really showing how far their reach is and what they can actually achieve in the setting to account for quite a broad range of observables, like the fact that the damping rate is maximal away from the phase transition and so on. It may be that something similar has been seen somewhere else, but that I'm not aware of.
And right. The symmetry rebreaking, that is observed in the experiment or not yet observed?
So I think they haven't looked for this, and we are thinking of actually following up. I'm told that the experiment no longer exists in this form, so it has to be restarted. But yes, this is something which may very well have been present, but it's really worth looking for again.
Sorry, I also had questions about semi-classics and numerics. And I was just wondering if you could, I mean, you avoided it a little bit, but if you could comment a little bit on quantitative agreement and sort of in which regimes, I guess, you would expect.
Right.
So I would think sort of if you have maybe high temperatures or high energies, then the semi-classics works better than if you're close to the ground state. Is that something that you see?
You know, you have to be realistic at some point about how well you know the system and how many things you can't control there. And I would be very hesitant to go very long distance towards trying to get a quantitative modeling of an effect of the largest cluster growing by less than 10%. That isn't to say that this isn't necessarily a worthwhile thing to do, but just the very natural first step in something like this is to use the fact that in the semi-classical effective model you can simulate huge systems, get the pristine behavior out, and then, a little bit like in Emmanuel's question, ask what are the sensible next experiments to do, which in this case would be to look very targeted way for the symmetry rebreaking, rather than trying to put a line through this here, because you do not need many fitting parameters to reproduce a line like that. So unless you've got a zero parameter theory, I would be relatively optimistic that I can fit this without being able to claim that the theory is actually the correct one.
Sure, thanks.
Question? Hi, thank you for this talk. Maybe a simple question to clarify my understanding. So the original experiment work done in like the Rydberg atom array is from an antiferromagnetic phase to a disordered phase. And here in your work is a parametric, FM phase to PM phase, right? Do you think that make any difference?
I didn't catch the one word. In our work,
the experiment work is FM to,
FM,
antiferromagnetic phase. Here is different setting. Do you think it matters regarding all this in-field picture description?
Okay, so I think from a sort of universal perspective, there is no different on the level of the modeling. Again, I'd like to emphasize, I probably went over this too fast in the beginning. Where was the experiment? So the experiment is not really from an antiferromagnet to a disordered phase. The experiment is from a translationally broken phase to an ordered phase. So the symmetry, Ising symmetry that's being broken is a translation by one lattice spacing and not, which of course is also the case in an antiferromagnet, but there's no Ising symmetry present here in the first place. Right, in this Hamiltonian. But since you're breaking an Ising symmetry, at the end of the day, the effective description is the same.
I see. Thank you.
Right.
Did you try looking at any correlations in like the X or Y components of the spin? I guess I'm mainly thinking about like spin squeezing type.
So
correlations.
The data is there. We haven't asked any questions in this direction. Of course, since you've got Z exchange and X field, X and Y are not, X and Y components of the spins are not equivalent, which is shown by the fact that this particular block sphere is not rotationally symmetric, but we haven't thought of any questions to ask. Perhaps you can help us a little bit. Yeah.
So because we're doing this experiment on a programmable simulator, in principle, we can think about more exotic scenarios, maybe if not that realistic, but we could think about a similar question for Floquet phases, right? We could think about quenching parameters in the drive and seeing whether we can restore say a time crystalline phase or modular issues with 2D stability of these phases. But is that a thing that you've thought about, or?
Yeah, so a little bit the talk I gave last week in the other program was morally Floquet problem whereas we had totally different starting points, some of the same ideas come about. So I think specifically the thing to look for may be these initial state-dependent spin echoes, which are so spin echoes for parts of the Hilbert space, but not the full Hilbert space, and to see how this would show up in a setting like this. Yeah, I think there are many directions that you could explore like that, and it is, as you say, one of the great things of the quantum simulators that you can change the quench parameters in a way that just wasn't possible before. Yeah.
Thanks.
Hi, thank you for the nice talk. I was just curious, also sparked by other question. If you would have a U1, like a magnet with some U1 symmetry breaking, would you expect this kind of re-breaking?
So, thanks. Yeah, you might expect that. So you can arrange for it to happen. This is unpublished work, but you can, I mean, there are different setups you can think of, but basically if you're sitting at the bottom of the Mexican hat, you can kick the thing around in various ways, yeah.
And is there a difference between having a long-range order or quasi-long-range order in that description?
Is there a difference between?
Between, say, BKT point or actual?
So I'm happy to announce on the basis of my mean field theory, there's absolutely no difference. Okay, so secondly, in practice, XY models are long-range ordered. Okay. And thirdly, so I think in most experiments that you're likely ever to see, you will not tell the difference. Thirdly, I think, so the way to analyze this then is to look at what the different length scales are, like the L of T length scale and so on. And then presumably you've got different regimes. Whether there's an intermediate regime which is qualitatively different, where you're where L of T is sitting somewhere within the, within some length scale characteristic of the vortex interaction, we haven't thought about, but yeah.
Thank you.
Yeah, thanks.
Question?
Yeah, thank you for a nice talk. So can you comment a bit more on the damping? So you had this picture of, like it depends on how spread you are in your initial state somehow, but can you understand it also as some correction to the mean field theory?
Yeah, so the actual theory that we used was a phi to the fourth theory with, some noise around it, which then feeds back to the dynamics of the order parameter. Yes, you can do this. It looks somewhat like the experimental system, but I'm not sure whether we really have a very satisfactory growth of the, decay of the order parameter coming out of that mean field theory, out of the mean field theory, out of the phi to the fourth theory of fluctuations that I think is really still a bit of an open problem, right? So in other words, the full description of the nonlinear dynamics of the fluctuations is not something that we really have in a satisfactory way on top of the mean field.
Great. Okay. Thank you so much. Yep.